Hello and welcome to helpyourmath.com. In this video, we are going to talk about finding probabilities of 1- and 2-part tasks with a focus on 2-part tasks and also a focus on using tree diagrams to help us. First, let's just start with the 1-part tasks. The results for simple 1-part tasks can be easily listed, such as listing the results of tossing a fair coin. The only outcomes are heads or tails, which we can abbreviate, since they have different first letters, to H and T. The possibilities of rolling a fair die, which is singular for dice, would be 1, 2, 3, 4, 5, or 6. Maybe let's consider a team with 5 members. We have Alex, Bev, Cora, Dave, and Eli. We might shorten this list. Conveniently, they all have different first letters, and conveniently, they're the first 5 letters of the alphabet. How about that? How many ways could a team captain be selected? We're going to assume this is just chosen at random. The 5 names are in a hat. And how many ways could a team captain be selected? There would be 5 possible ways, right? It could be any one of the 5. What is the probability Bev will be team captain? So we might say the probability of Bev, well, there's only one way for Bev to be selected, and there's 5 possibilities. So there's a 1 in 5 chance Bev will be team captain, or we could say a 20% chance. And that's 1-part tasks, And one more example. A box of 20 chocolates has 2 dark chocolates, 12 milk chocolates, and 6 white chocolates. What is the probability that you randomly select a milk chocolate? So let's say you have your eyes closed, right? Because the colors would probably be different. You're closing your eyes, you're like, I want that one. Well, how many, let's see, so we're gonna call this P of M for milk chocolate. And how many favorable outcomes are there? 12, because there are 12 milk chocolates in this box. And the total, it says there's 20, and we could check the work. 2 plus 12 is 14, plus 6 is 20. So we have a 12 in 20 chance. If we divide these by 4, we get 3 out of 5. So there's a 3 in 5 chance, or a 60% chance. So more likely than not that you will get a milk chocolate if you blindly select a chocolate. Now let's move on to 2-part tasks. So 2-part tasks, of course, are, 2 things happening, and 2 things can happen either at the same time or at 2 different times. If they're at the same time where one outcome is not dependent on another, we call those independent events. 2 events are independent when the occurrence of one does not affect the probability of the other, such as tossing 2 coins or rolling 2 dice or tossing 1 coin and 1 die. Whatever happens on the coin will not affect rolling a die. These are called and probabilities. What's the probability of flipping heads and rolling a 3? 2 events are independent if the occurrence of one does not, okay, I already said that. Consider 2 independent events A and B with individual probabilities P of A and P of B. The and probability that A and B occur is just the product of their individual probabilities. This principle can be extended to any number of independent events. So if there's event A, B, and C, we would do the same thing. We would multiply the 3 probabilities together to get the probability of all 3 of these things occurring. All right, so what is the probability of flipping 2 heads in 2 coin tosses? The probability we flip a heads in the first coin toss is 1/2. I'm going to call this heads 1. The probability that the second coin toss is a heads is 1 out of 2. The probability that they're both heads would be heads 1 and heads 2. What do? We multiply the probabilities. That would be 1/2 times 1/2. There's a 1 in 4 chance. And this is true of anything where there's 2 outcomes that are equally likely, such as if you're taking a true or false test. What's the probability if you just randomly guess true for 2 of them that both will actually be true? There would be a 1 in 4 chance. What is the probability of rolling 3 6s? So we're going to apply this now to 3 events, 3 6s in a row with a single die. So we roll the die once, we observe it, twice we observe it, 3 times we observe it. The probability of the first one being a 6, I'll call that 6 of 1. That would be there's 1 way to get a 6 on 1 die, and there's 6 possible outcomes. The probability of the second die being a 6 is 1 out of 6. And the probability that the third one is a 6 is also 1 out of 6. So they do all have the same probability, right? Because I'm not changing the event. Therefore, they would have the same probability. What do we do with these 3 probabilities? For the first one to be a 6 and the second one and the third one, we multiply them. So the probability of 6 and 6 on the third one is 1 over 6 times 1 over 6 times 1 over 6. And this we call repeated multiplication. We could also use an exponent if we wanted to, because there's 1/6 being multiplied, repeated 3 times. This would give us 1 out of 216. I'm not putting the decimals. I could put the decimals or the percents. I'm just keeping it fractions because, you know, there's several problems and I like fractions. So we have 1 out of 216 would be the chance of rolling back-to-back 6s 3 times. A little more with two-part tasks. Those were independent events. Again, whatever happened on that first roll does not affect what happens on the second roll, which does not affect what happens on the third roll. Let's talk about when there is dependence and probabilities with dependent events. Two events are dependent if the outcome of one does in fact affect the probability of the other event. Consider two dependent events A and B with individual probabilities of P of A and P of B. The probability that A and B occur is the probability of A and B. So again, we would start with the probability of A, then times the probability of B happening given that A already happened. So that one's going to be a little bit different. It won't just be the probability of B, where probability of B given A means the probability of event B given the occurrence of event A. This principle can be extended to a number of dependent events. Let's go back to our chocolate example. A box of chocolates, we already talked about this, was the probability that you select one and it's milk chocolate, and then you select a second one and it's also milk chocolate. Because you've already eaten one, the probability of the second one being milk chocolate is now affected, both the numerator and denominator. So we'll start with the first one. We have the probability that the first one selected is milk chocolate. There's still 20 in the box. This would be our 12 out of 20. I simplified it earlier. You know, at some point we can simplify. I'll simplify it now. That was 3 out of 5. But now we're looking at the probability that the second one is milk chocolate, given we already had a milk chocolate taken out of the box. So now if there were 20 and I pulled out a milk chocolate, now there are 19 left in the box. So the denominator becomes 19. And the number of milk chocolates decreases by 1, right? Because 1 was taken out. Now there's only 11 left in the box. The probability of the second one being milk chocolate, given the first one was milk chocolate, is now 11 out of 19. So what we would do is we would multiply these probabilities. We get 3 over 5 times 11 over 19. I already simplified. There's no more simplifying to happen. I'll multiply straight across. We get 33 out of 95. So it looks like just about a third. I will convert this because this fraction isn't as easy to read as some of the others. And yeah, we get just about a third. We can say 0.347, or you could say 34.7%, whichever way you're asked to do or whatever way makes the most sense to you. But the probability, you select a milk chocolate and then you select a second milk chocolate, it's about 1 in 3. We could also rephrase the question where it might say the first one is milk chocolate, but the second one is dark chocolate. If we were going to look at that, so first milk, second dark, this would still be dependent events because we still need the milk chocolate to happen on that first time we're the first selection. So in this case, the probability of the milk first would still be 3 out of 5. I'm just going to reuse that. But now the probability that the second one is dark given the first one, so dark given that milk already happened, again, we did take a chocolate out, so there are only 19, but we haven't taken either of the, sorry, I'm getting ahead of myself, but we haven't taken either of the two dark chocolates out, so there are still both dark chocolates, and then we would multiply 3 out of 5 times 2 out of 19. Still can't simplify. We get 6 out of 95. This one's a lot less likely. 6 out of 95, we get 0.063-ish, roughly. And the likelihood of this is about 6.3%. One way we might organize especially dependent events, but 2 or 3 part tasks, or really 4 or 5, although it tends to get messy, is using a tree diagram. Tree diagrams are especially useful when we have 2 or 3 part tasks. We put the probabilities above the branches for each task. Tree diagrams can be displayed vertically or horizontally. More common, we use the horizontal. It's rare we would use vertical. So we just start with the thing, and then we kind of split up the branches, and then along the branches here, we would say there's 1/2 chance and 1/2 chance, or whatever the probabilities are. So how could I represent this chocolate scenario using a tree diagram? All right, so we have our box, and this is going to say chocolates. Okay, and so what could happen? You reach into the box, and what are the 3 possible outcomes? You get a dark chocolate, a milk chocolate, or a white chocolate. So we have 3 different branches to represent each of the possible outcomes. And then usually, and if we can, we would use a single capital letter. If we have to differentiate some other way, you know, if 2 of them started with the same first letter, maybe we use the first 2 letters, but somehow we have to say what we're doing, how we're representing it. Okay, so then the dark chocolate, and we're going to put the probability along the branch. You can leave it unsimplified or you can simplify it. Dark chocolate, there's 2 out of 20. So I can either write 2 out of 20 or I can put 1 out of 10. Milk chocolate was 12 out of 20, which I can either just say 12 out of 20 or 3 out of 5. And white chocolate is 6 out of 20. I can simplify that to 3 over 10. Now, what should happen is when we have 3 branches stemming from the same point, those probabilities should add up to 100%. So one of those things must happen. We could check our work as long as I assume, well, I don't assume, I know that 3 out of 5 is 6 out of 10. 1 out of 10 plus 6 out of 10 plus 3 out of 10 is 10 out of 10. There's my 100%. Now what we do next is we do the second branches for the second selection. So these are the outcomes for the first selection, but now we have 3 different scenarios, right? We could select a dark first, a milk first, or a white first. If we start with the dark, there are still 3 options that could be selected second. We could have a dark chocolate and then a dark chocolate and a milk chocolate, a dark chocolate and a white chocolate. So all 3 of these are still possibilities. We get 3 branches, and then we would say this is the second. Now when we go to do the probabilities, these are all stemming from the fact that we are assuming a dark chocolate was chosen first. So we have to keep that in mind as we go through. If a dark chocolate was chosen first, that means that there's only 1 dark chocolate left, and there's only 19 chocolates by the second selection. The probability that the second one would be dark chocolate would be 1 out of 19. And then here, the probability of a milk chocolate, there's still 12, right? Because the first one was dark. So this would be 12 out of 19. And the white chocolate, there were 6, still 6 in the box. We would have 6 out of 19. So one check is we could make sure we have 100% of the possibilities happening. 1 out of 19 plus 12 out of 19 plus 6 out of 19, that's 100%. I like it. And then the way we use the tree diagram is we could put the probabilities of each event right behind the very last column that we would have. So because we're talking about selecting 2 chocolates, we would just put the probability right here. So this, my screen's going wonky. This D right here represents dark then dark. So that's what that means. That's how we would read this, starting from over here in the box of chocolates. Going up this branch means the first one was dark. Going up this branch means the second one was dark. And then we can multiply 1 over 10 times 1 over 19 gives me 1 over 190. So there's a 1 in 190 chance that I'm going to select the 2 dark chocolates. The second branch, right below it, this would be the probability of dark then milk. Sorry, my question disappeared. All right, so this is dark then milk, and then we could put the probability here. It would be 1 in 10 times 12 out of 19. And this we have a 12 out of 190 chance of happening. And then we could do the same thing, dark first, white second. This would be 1 out of 10 times 6 out of 19, which would be 6 out of 190. Now we do the same thing with the milk chocolate. I know I'm doing more than the question asked me to do. I'm just wanting to show how this tree diagram works. We can also see these can spread out, right? These are tree branches and they each have 3, so they're growing fast. So I'm going to have to kind of like make some adjustments here. All right, so for my milk chocolate, if I select a milk first, the 3 possible outcomes for the second, we could select a dark second, a milk second, or a white chocolate second, right? So all 3 of those chocolate flavors are still on the table. This time we selected milk first. So in the purple, we still have 2 dark chocolates. We only have 11 milk chocolates left, and we still have 6 white chocolates. There are now 19, just like the top second branches. There are still 19 in this scenario because there was just 1 selected. So dark chocolate, we still have 2 in the box, and there's 2 out of 19 that we're going to get the dark chocolate. With the milk chocolate, there are 11 left, and that would be 11 out of 19. White chocolate, there are still all 6 there, would be 6 out of 19. And we could do these probabilities again. We could have this branch, we go from milk to dark. So this means we select a milk and then a dark, and we would again multiply 3 out of 5 times 2 out of 19, and we get 6 over 95. These denominators are different because of that first probability where I was able to simplify it a little bit more than the dark chocolate 1 in 10. This one has 3 and 5. So they are a little bit different, but it still works. And then we should see this milk then milk. This should be the same answer that we had before. 3 out of 5 times 11 over 19 is 33 over 95. And this one is milk then white chocolate. And this one would be 3 over 5 times 6 over 19, which would give us 18 over 95. All right, the last one. What happens if we choose a white chocolate first? We would still have all 3 flavors left to choose from for our second option. I suppose if we did a third one, which I absolutely will not be able to squeeze onto this slide, we wouldn't need to do a dark, then dark, then dark, because that would be impossible because there are only 2 dark chocolates in the box. But that's pretty rare. Usually we always continue to have the same number. So if we start with 3, we continue to have these 3 possible outcomes. But it is possible that we wouldn't. So this tree is going to go real wonky tonk. We could select a dark, a milk, or a white chocolate second. And then now this time we select a white first. So we still have the 2 dark chocolates. That would be 2 out of 19. We still have all 12 milk chocolates. That's 12 out of 19. We selected 1 white chocolate already. Now there are only 5 out of 19. Check the numerators, make sure they add up to 19. They do. Okay, good. And then our last 3 probabilities, if we have white, then dark, this would be 3 out of 10 times 2 over 19, which is 6 over 190. If we have a white, then a milk chocolate, that would be 3 out of 10 times 12 over 19, which would be 36 over 190. Oh, this one we can simplify, right? The only one, because the 12 and the 10 have a common factor, so we could simplify this to 18 over 95. But again, usually it's fine to just leave it as 36 over 190. And then last, if we have a white, then a second white chocolate, this would be 3 over 10 times 5 over 19, which would be 15 over 190. And then if we added up the 3 red probabilities, the 3 purple probabilities, and the 3 blue probabilities, it should add up to 100% because we're encompassing all possible options. But this is just another way we can organize our information. It's supposed to be neat, but because there were 3 outcomes, it tends to grow quickly, so it does get a little bit out of control, and we just have to be really careful with this. So going back to our flipping of the 2 coins, because this one will be a little bit, I can probably make this one a little bit neater. All right, so we have the coin. Here it is. It's so cute. It's clearly on heads right now. But this coin, we could have one of 2 outcomes. We could flip and it lands on heads. We could flip and it lands on tails. The probability that it lands on heads is 1 out of 2. The probability that it lands on tails is also 1 out of 2. Now, the second flip is not at all dependent on whatever happens first, right? It doesn't matter whether it landed on heads or tails first. You're going to flip it again, and the probabilities don't change. So this time we could flip heads first, and we could flip heads second. The probability of the second one being heads is still 1 out of 2. The probability of it landing on tails second is also 1 out of 2. We could flip tails first, and then we could flip a heads, or we could flip a tails. So we're just listing all the possible outcomes. And because these are independent activities, events, we don't have to worry about any weird subtraction like we did with the chocolates. And then just like we did with the chocolates, we could go along, and as long as we're moving horizontally, we would multiply the probability. We would multiply the probabilities. So this one, this heads right here is saying we flip a heads and then we flip a second heads, which I can abbreviate. I don't need to write the then here. I can just say HH, and this would be 1/2 times 1/2. That would be 1 times 1 over 2 times 2, 1/4 for heads. The probability of flipping a heads then a tails would be 1/2 times 1/2. Spoiler alert, everything here is 1/4. This one's tails then heads. Also 1/2 times 1/2. These get a little boring, don't they? Sorry. And then lastly, tails and tails would be 1/2 times 1/2. But we could use these. I could ask all sorts of different questions. What's the probability that the two coins won't land on the same thing? And then you would just look at the middle two and say, well, there's a fourth here and a fourth here. So therefore there's a 1/2 chance that they'll be opposite. It'll land on opposite sides. One last example. A bag contains 8 blue marbles, 4 red marbles, and 6 purple marbles. 2 marbles are drawn from the bag without replacement. Without replacement means one is drawn and then not put back in the bag. So we're not drawing 2 at the same time. We're doing 1, looking at it, observing the color, and then whatever, throwing it in the trash. I don't know what we're doing with this marble. Whatever we're doing, it's not going back in the bag. Let's draw a tree diagram, and then we can talk about all the different probabilities. Actually, I think there's some questions. So I won't do all the probabilities, but I will set up the tree diagram. I encourage you to pause the video and you try to set up the tree diagram yourself. Okay, so I'm going to start. I'm going to have my bag, and you should know I am not an artist. Art was not my thing. There's my bag. Okay, we have blue marbles. How many marbles are in the bag? Oh, it doesn't tell us. So we're going to add them up. 8 plus 4 plus 6. 8 plus 4 plus 6 is 18. So there's 18 marbles in the bag to start. I selected blue marble. The probability I selected blue marble would be 8 out of 18. I'll leave these unsimplified for now, just to make my life a little bit easier, maybe. The probability I select a red marble, there are 4 red marbles. That would be 4 out of 18. The probability I select a purple marble is 6 out of 18. Just to double check, because these are all from the same little point here, these should add up to 18 over 18. They do. I feel good about that. Now what happens next? We pulled a marble, we saw it, we threw it aside. We're going to draw a second marble. I could have selected a blue marble first, and I have 3 options that could happen second, right? I could select a blue marble again. This time, because I already selected a blue marble, there are now only 7 blue marbles left in the bag, and there are only 17 marbles left in the bag because I already selected one, observed it, and did not put it back in the bag. If I select a blue first, the probability that the next one is red, I still have all 4 red marbles, and it'll be 4 out of, but I did select 1, so there's still 1 missing. My denominator would be 17. Lastly, I could select a blue marble first and a purple marble second. There were 6 in the bag. There are still only 17, right? Because we're still just, this is all the possibilities of what could happen if a blue was selected first. And now we repeat this process, but this time we're saying we selected a red marble first. I could select a red first and then a blue second. There are still, now we go back, right? Because now I selected a red marble, all 8 blue marbles are still there. I have an 8 in 17 chance of selecting a blue marble second. I could do a red marble and then a second red marble. One of these is gone in this scenario, so now there's only 3 left, and that's 3 out of 17. Or I could have red then purple, and if I do red then purple, there are still 6, so I would have 6 out of 17. And now to try to squish the purples, I could do a purple first. I'm going to put these, I'll just do them on the other side. Why not? And I could select a blue second. Let's see, there's still all 8 blues, so this would be 8 out of 17. I could select a red second. All 4 reds are still there, so it would be red, 4 out of 17. Or I could Or I could do purple, then purple. I did select a purple, so now there's only 5 purples left in the bag, and this would be 5 out of 17. So if I had the space, I would have done it, much more so it was all vertical, but I just kind of had to adjust for the room because there were some follow-up questions. Pause the video, see if you can get these 3 questions, see how you do. Where are you getting stuck? Go ahead. Okay. What is the probability that 2 blue marbles are selected? So what this means blue, then blue. How do we figure this out? Well, we would go starting at the bag, and we go up blue, then blue, and we multiply the probabilities because these probabilities mean given blue happened first. So blue, then blue would be 8 over 18 times 7 over 17. Now I might simplify before I multiply. 8 and 18 have a common factor of 2, so we would simplify to 4/9. Now we have 28 over something, 153. You could leave it as a fraction. Maybe we write it as a decimal just because it might be a little bit easier to interpret as a decimal. 28 divided by 153 is 0.183. So it's like, just shy of 20% chance that both marbles would be blue. What is the probability that a red is drawn first and a purple is drawn second? What is the probability a red is drawn first? So this is red, then purple. And for red, then purple, the red is first, the purple is second, so we're following that path. That would be 4 out of 18 that red happens first, times 6 out of 17, the probability that purple happens given red already happened. I can simplify the 6 and the 18. 6 goes into itself once and 18 3 times. Now I can multiply straight across and I get 4 over 51. And again, I might convert this to a decimal just because that might be a little bit hard to interpret. We get 0.078. So there's like a 7.8% chance. What is the probability that a purple is drawn first and a blue is drawn second? So we have purple, then blue. We're kind of going backwards here. And that would be 6 over 18 times blue second, given purple first, would be 8 over 17. Let's simplify this. We get 1 over 3. This one's 8 over 51. So twice as likely as the one right above it, right? Because that was 4 out of 51. So this one we could also say is 0.15. Beautiful. Thank you for stopping by and watching this video on my kind of awkward looking tree diagrams. They should look much nicer, but it's hard to give them enough space and then also ask follow-up questions. If you have any questions, leave a comment, or if you know my email me. I know these can be a little bit weird, but I also think they're really fun. So hopefully you have fun with them too.